Hey, this is Mr. Janes, and this is the second video on ratios and proportions and how they work with geometry. In this video, we're going to be talking about these last three application problems on the back side, on the bottom of the note sheet. These three right here, 1, 2, and 3. At this point, if you haven't already tried these, please pause the video now and give them a try. Remember, please pause the video. We'll be going over these in 3, 2, 1. All right, taking a look at the first one. The most important thing about these kinds of problems is to consider what two quantities, what two values are being related to each other. So let's take a look and I'll show you what I mean. The first problem says the ratio of AB to BC is 3 to 8. Solve for x. Well, here we've got this diagram and they have AB and BC labeled, so it seems like we are comparing the length of AB and the length of BC. So let's just put that as a ratio right here so we don't forget the two things that we are actually comparing, AB to BC. Okay, so what ratios do we know about AB and BC? Well, we know that the ratio is 3 to 8. They told us that in the beginning, 3 to 8. We also know by looking at the diagram that the actual size of AB is 6, and that the actual size of BC is x. That's what we're trying to find. So we'll write that here. Remember, AB over BC, just like we talked about in the beginning. Now we've got a familiar proportion that we can go ahead and solve. We'll end up with 3x equals 8 times 6, which is 48. We'll divide both sides by 3, and we're left with x equals 16. Now, before we finish, we double check that 16 does in fact work. And so all we need to do is plug 16, or substitute 16, back in for x here. And so that'll mean 3/8 equals 6 over 16. Does that make sense? Is 3/8 the same as 6 over 16? Well, yeah, if we take the fraction 6/16 and divide both the top and bottom, the numerator and the denominator, by 2, then we would end up with 3/8. So yeah, those are equivalent fractions. Those are the same. Let's take a look at the second problem here. The distance from Hartford to Palm Beach is 5.6 inches on the map below. Okay, so this is 5.6 inches on that map. The scale on the map tells us that 1 inch is 200 miles. What is the distance from Hartford to Palm Beach? So again, we have to think about what two values are being compared here. And the two values that are being compared must be what looks like the distance on the map distance, which is in inches, and the distance in real life, which is in miles. And so all of the ratios we write in this proportion will be of that form. So let's think here. They tell us that 1 inch is 200 miles. So 1 inch on the map, and draw a ratio to 200 miles. Well, we also know that Hartford Palm Beach is 5.6 inches on the map, so that'll go in the numerator, 5.6 inches. And we don't know the real distance, so we'll call that x in miles. Now we've got a proportion that we can work with. That'll be x times 1 is just x, and 200 times 5.6 gives us 1,120 miles. Again, we multiplied 200 and 5.6 together to get that number. And there's no coefficient on x, so this is our answer right here. The distance from Palm Beach to Hartford is 1,120 miles. And that seems like a pretty reasonable answer for a distance basically from the north end of the country to the south end. Last but not least, Lego figures are 1.5 inches tall. That's these guys right here. It's a little Lego figure. And the average person is 5.5 feet tall. Let's actually start labeling this here, right? It's 1.5 inches for this little guy, 5.5 feet for the average person. Yoda from the Star Wars movie, or from the movie Star Wars, this guy right here, is 2 feet tall. So he's 2 feet. If the Lego company wanted to make a Yoda figure, how tall would it need to be? So that's what we're trying to figure out. How tall should this be? Well, it makes sense for this Lego Yoda to be in proportion to, I guess, the regular Yoda. So we ask ourselves, what two things are being compared here? Well, you might say that the real life figures, the real person, the real Yoda, are being compared to the Lego figures. So let's write that down. So we're comparing the real people, and those are measured in feet, how tall they are, to the Lego people, which are being measured in inches. And so we can write a proportion that follows that form. Let's start with this person over here. So he's 5.5 feet tall. And the Lego guy right here is 1.5 inches. Similarly, Yoda, the real Yoda, is 2 feet tall. Again, that's going in the numerator. And we don't know how tall Lego Yoda is going to be. We do know it's going to be in inches. So if we solve out our proportion here, we'll have 1.5 times 2 equals 5.5 times x. 1.5 times 2 is 3 equals 5.5x. We'll need to divide both sides by 5.5. And we find that x is equal to about 0.5454 repeating, so we'll round that to about 0.54 inches. That's how tall this little Lego Yoda should be. Now, if you'd done this yourself, you might have said, well, Mr. Jaynes, I didn't compare the real people to the Lego people. I compared the people, the people here, to the Yodas, right? So I compared the people to the Yodas, right? These two guys. And you can do that too. We could say that the tall person is 5.5 feet tall, and the Yoda was 2 feet tall. Similarly, this toy person was 1.5 inches tall, and this toy Yoda, well, that's X. We're not sure about that yet. And the nice thing about this is it doesn't matter how you set it up, whether you set it up this way or this way, because if we go ahead and cross multiply, or I don't really like that word, if we simplify this, we get 5.5x equals 3, which is the same exact thing we had up here. Either way, you'll get x equals approximately 0.54 inches for this little Yoda figurine. This is the end of part 2 of the ratios and proportions video. I hope that you've understood it. If you have any questions, make sure you bring those to class and prepare for a video check.